What if you could write a plant's entire life story before it even sprouts? What if you could know, just by using a bit of code and some weather data, exactly when it's going to be ready to harvest, or maybe more importantly, when it might fail? Well, it's not science fiction, it's just math.
So how do you do it? The answer is in what you could call its biological source code. Today, we're going to dive into a model that uses just 15 equations to simulate the entire life of a lettuce plant. It's called a phenology model, which is really just a powerful way to translate biology into the language of mathematics.
So here's the game plan. We'll start with the absolute engine of all plant growth. Then, watch our digital lettuce climb the ladder from a tiny seedling all the way to maturity. And then, we'll get to the dramatic part, a race between a successful harvest and a process called bolting. Finally, we'll put it all together and see the model in action.
All right, every story has to start somewhere. And for a plant, that story is powered by one thing above all else: energy. Specifically, the energy it gets from heat in its environment.
The model has a name for this energy: thermal time, or growing degree days, GDD for short. Honestly, the best way to think about it is like a daily energy budget. Every single day, the plant collects these little heat units based on the temperature, and it saves them up to spend on growing bigger and stronger.
So how is this energy actually calculated? Well, this is where the math shows us the plant has a real Goldilocks preference. See, in that perfect optimal temperature range, the calculation is pretty simple. But if it gets too cold or way too hot, the formula gets more complex. It adjusts to show that the plant is struggling and isn't using energy as efficiently. It needs things to be, well, just right. And that brings us to the master equation for daily progress. Our thermal time is the fuel, right? But it gets multiplied by these three other factors that act like accelerators or brakes on that engine: temperature, day length, and stress. Let's take a look at a couple of those accelerators. First up, the photoperiod factor. Lettuce is what's known as a long day plant. So what that means is, once the amount of daylight crosses a certain critical threshold, its development literally speeds up. It's a biological signal screaming, "Summer's here!" And as we're about to see, that can be a real double-edged sword.
And then there's the stress factor. This is pure survival instinct written as an equation. If the plant gets stressed out, say from a drought, it hits a panic button. This formula accelerates its development in a desperate dash to reproduce and create seeds before it's too late.
Okay, so our digital lettuce is collecting energy every single day. But how does the model actually use that energy to track its physical growth and hit all those key milestones? It's all about saving up. This formula is beautifully simple, but it's absolutely crucial for tracking progress. See, each stage of life, from seedling to mature plant, has a specific energy cost, a required GDD. The model is just constantly checking how much energy have we saved up versus how much do we need.
And this illustrates it perfectly. You can think of it like the plant is filling up an experience bar in a video game. Once that bar hits 100%, boom, it levels up and moves on to the next phase of its life.
So how does all this digital progress turn into actual visible growth? Well, this part is just so elegant. The internal stage names the model uses, like V7, they're not random at all. The model simply reads the number right out of the stage name. V7 literally means the plant has 7 leaves. It's that direct.
But, growth isn't always easy. As the lettuce gets older and more mature, making new leaves actually starts to cost more energy. In this case, it's 1.6 times the base requirement. It's a great reminder that, just like in life, things can get a little harder with age.
So our lettuce is growing up, it's doing well, but now it enters the most dramatic part of its entire life, a high-stakes race. It's a race between forming a nice, harvestable head of lettuce and bolting, which is when it gives up on leaves and shoots up a flower stalk instead. And for a farmer, believe me, bolting is bad news.
Okay, so to even start this race, the plant has to pass a critical check. Does it have enough leaves to even think about forming a head? The requirement here is 12 leaves. Our plant has 13, so the model flags can form head as true, and the race is officially on. Now let's meet the antagonist in our story, bolting. The model doesn't see this as a simple on or off switch. No, instead, it's smarter. It tracks 4 distinct danger signals that slowly add up and increase the plant's total risk of bolting over time. Danger signal number 1, long days. Hey, remember that photoperiod accelerator we talked about? Well, here's its dark side.
Every single day that the day length is over a certain threshold, it adds a little bit to a cumulative bolting score, pushing the plant closer and closer to flowering.
Danger signal number 2, high heat. It's a very similar idea. When the temperature climbs above its own threshold, it also adds to that bolting risk. Heat is another powerful stress signal telling the plant, hey, it's time to reproduce now.
Now, danger signal 3 is the real combo move. If both the average temperature and the day length are high for a sustained period of time, the model adds a significant chunk of risk all at once. A long hot spell is basically a massive red flag.
And the final danger signal is simply age. The more leaves a plant has past a certain point, the more naturally inclined it is to bolt. This is just a plant's internal clock saying, okay, I'm mature now, it's time for me to complete my life cycle.
All right, we've looked at all the individual rules, we've seen the equations. Now let's step back and see how this powerful simulation actually works when all the pieces finally come together.
And this is the daily loop that runs over and over. Every day, the model calculates the energy budget from the weather. It uses that energy to track growth, it checks if the plant can form a head, and it's constantly updating that bolting risk. These 15 equations all work together, day by day, to write a dynamic, living biography of the plant's future.
So why does all this matter? Well, by translating biology into math, we can build incredible tools to help farmers make better decisions, optimizing when to plant, predicting their harvests, and managing all kinds of risks. And honestly, that is absolutely crucial for food security, especially in a changing climate.
We've just decoded the fundamental rules for a single head of lettuce. It just makes you wonder, what's next? An entire ecosystem? The spread of a forest? If we can write the source code for one little plant, what other parts of the natural world are we ready to simulate?